Welcome back. We now have a nice summary table of all the log properties. Our first one, log base b of 1 is 0. So as long as b is positive and is not 1, and remember 0 is not positive, so that is excluding 0, then if we're taking the log of 1, it will be equal to 0. Log base b of b, we know there's the invisible first power, so we get 1. Now I want you to look at log base b of b to the p now that we know our power rule. Well, I can put that power down, so it would be p times log base b of b, and now I'm just using the second property. Log base b of b is 1, so I get p times 1, which is p. Now 4 here is a little bit weirder, but this is making use just the same way 3 is of the fact that these are inverses. So b to the log base b undo each other just like the square root of a thing squared. And then we have our product, quotient, and power properties. So we've already been making use of these in the way that I've, especially the ones at the end of the problems, those are the ones I make up, into how we can expand it out and use these properties kind of in conjunction. Now, the whole shebang, everything. Now, I do want you to note, though, up here, at this point, we've learned 7 properties of logarithms. The properties hold true for the values of the variable for which logarithms are defined, i.e. positive and not 1. Therefore, in the examples and exercises, we will assume that the variable expressions within the logarithms represent positive real numbers. So it's okay to have a 1 inside, it's just not okay to have a 1 as the base. But this now means they're not going to write after the problem, assume all variables represent positive real numbers. They just got tired of writing it. But when we get to the next section, oh, just kidding. Now you need to double check. But first, I have the log of one ugly mess. I want to take this and expand it out. So this can get pretty crazy. And I would say until you're very comfortable, you should do this slowly. I know that sounds extremely painful, but when you're learning, do it slow and careful. As you get more practice, then you'll get quicker at it. And as you can see, if you sneak a peek at the next example, that one is compression. We're going to put it all back into one logarithm. But here first, write the expression as the sum or difference of logarithms. All right. So a couple ways to think through this, but I'm going to take it slow to start with. So I have log, just regular log base 10 because I'm lazy. So overall, one of the ways to figure out like how you're doing this is to figure out what your order of operations would be. So here, inside the parentheses, I would do that first. Within that, I would do the a to the 4th first, then I'd multiply that by b and divide it by the c to the 9th would be calculated. But overall, the division is the second to last step. So that's the first one I want to use my log property on. So I have the log of a fraction. So I'm going to break that into a difference. So I have log of the top, which is a to the 4th b, minus the log of the bottom, which is just c to the 9th here. Now, if there was more than one thing on the bottom, I could write it as a product here, and then like we saw earlier with the EY, then they would each get their own log with a minus sign. You might also stretch your brain and remember, we can rewrite stuff on the bottom of a fraction as something on top with a negative exponent. So this c to the 9th is also the same as times c to the negative 9th, where my exponent is negative and it's moved up. But here I have my minus in front, but in a minute we're going to power that 9 down and it'll be the negative 9, the same one we'd get from the other direction. So like I said, if you know your exponent rules, you can actually work your way through to remembering some of the other rules. All right. So the log of a to the fourth b. Before I deal with the powers, I want to deal with the product here first, because that fourth power is not on the b. So I need those separated before I can use my power down rule. So now we are just going to break this into the log of a to the fourth plus the log of b minus the log of c to the ninth. And now power down. The b has an invisible 1, which moving it so we're multiplying by 1 does nothing. And now this is 4 times whatever the log of a is plus whatever the log of b is minus 9 times whatever the log of c is. That is a sum or difference of logarithms. And then the directions you're going to see online, they'll also say with no exponents that aren't 1. Meaning you also have to bring down all the exponents. So you use the 3 big rules that I've gone over. And you know you're done when the only thing inside the log is a single number that can't interact with the log in any way, or a single variable with no exponents, just an invisible 1. All right. Okay, so now we have ugly mess number 2, which yes, very much has the dear God, why? Because the book might throw something this ugly, so let's handle it now. So I have log base 5 of the cube root of 25 divided by a squared plus b squared. Good Lord. First things first, we have a cube root of a whole ugly mess. That's the first thing I want to deal with log-wise, because it's the last thing I would do before I apply to log if I was going to calculate here. So this is the same as log base 5 of ugly mess to the 1/3 power, just like we did the 1/5 power earlier. So we power down. So I now have 1/3 times log base 5 of ugly mess. So since the 1/3 was applied to everything inside, we're going to see that 1/3 end up needing to be distributed everywhere. So it'd get a little tedious, but that's the way it works. All right. So now the next, or the last operation I would do, I'd figure out all the stuff in the parentheses, then I'd square that result, and then I'd do 25 divided by that. So I'm going to deal with the fraction next. Fraction turns into the difference of logarithms. So we have, I'm actually going to write the 1/3 out front, and I'm just going to put these huge brackets because I write big. So this becomes log base 5 of 25 minus log base 5 of the very weird looking a squared plus b squared. Now, when you're doing log problems and you see something like this where it's binomial or trinomial squared, do not FOIL that out, because logs are going to pull our powers down outside. And if you multiply it all out, it won't work anymore. So if your brain had that thought like, oh, I'm going to have to do that, not on log problems. All right. So my second one here does have a power that can come down. My first one here, log base 5 of 25, should hopefully be, that interacts. It does indeed. So let's recopy the ugly 1/3. And this is indeed now log base 5 of 5 squared. So it's just going to become a 2 minus, now that 2 comes down. And this is log base 5 of a squared plus b. Now this a squared plus b, I did not have a property that took the log of a sum and made it, I don't have an operation that's less than addition. I kind of think of it as like addition, and then repeated addition is multiplication, and the repeated multiplication is exponents. So they kind of form this hierarchy, but there's nothing below addition, at least not in any normal math. Who knows? Maybe in fancy math there is. So when I have the log of a sum, I can't do anything. Even though if it was just the log of a squared, the power would come down because I have an addition after in terms of order of operation. That's my outermost one. I can't break it anymore. So that term is going to stay just like that. This guy over here is just going to be a 2. And then they all get multiplied by the 1/3. So this instead of 2 now is 2/3. And just the coefficient up front gets that 1/3. So it is also 2/3. You could technically write it all over 3. You can also just leave it as a 1/3 up front. Alex should take that. But this a squared plus b, you must put the parentheses. If you don't put the parentheses, then it's going to think the plus b is not inside the logarithm. So this is one of those where you have to be careful. You have to know how Alex thinks more or less. So safe math, use your parentheses. All right. Now a little more interesting. Since we haven't done the change of base formula, yes, they deliberately hold it till the end. It's kind of annoying. I don't have a way to just crunch this in the calculator, but it's all functions and numbers. So this should be calculable. I should be able to get a number at the end of this. And indeed, the book actually deliberately picked the numbers to interact nicely. So they give us a hint. Write the expression as a single logarithm and simplify the result if possible. So written separately like this without the change of base formula, well, those don't interact. Log base 3 of 10, I can't write 10 as a power of 3. So, but I do know log base 3 of 54 plus log base 3 of 10, that plus, if I multiply the two numbers that the logs are applied to, then it becomes one logarithm. So those guys are going to become log base 3 of 54 times 10. Now, the caveat here is it does need to be the same base, but the book is not going to give you anything with different bases, not for college algebra. Like separate problems will have different types of logs, but within a problem like this, unless they're just wanting you to simplify it, but not for compressing back together. All right, and now I have minus, so things that are negative end up coming under by division. So I now have 1 logarithm. And I didn't bother to multiply it by 10 because I knew it was going to crunch up nicely. So 54 times 10 divided by 20. Well, the 10 and 20 cancel out, so it's just 2 on the bottom. And then 2 goes into 54 27 times, which is a power of 3. "27 is indeed 3 times 9. So that is 3 to the third. So the log base 3 of 3 to the third is 3. So all that crazy work for 3. It's probably the most complicated way you've seen 3 written. It could be done more complicated. That is not a challenge or a dare. All right. So we just did compression with numbers. Now we're going to do the same thing, but we also have some exponents to deal with. So we're going to be undoing our power down rule. We're going to be undoing our sum and difference rules so we can smush it all together as one logarithm. On these, it's kind of rare for them to interact. They could do it, it just, yeah. Alrighty. So first thing then, since the last step we did when we were expanding was the power step, the first thing we're going to do here is power everything back up. So this one is going to become now log of x to the third. Now, the way you power these up, like, can go either way. So you could move it up as -1/3, and then you would have a plus there, or you can leave the minus and then just move the 1/3. And that's what the book typically does. It doesn't usually like to see negative exponents. So this is what the book would have as an intermediary step. So we have minus the log of y to the 1/3 minus the log of z to the 2/3. And I'll deal with those once we get it all smushed together. So now I have the log of x to the third, that one's positive, minus another log, so this can be compressed. They're all the same log, it's just pluses or minus, there's no extra numbers in front. So now the log of x to the third will go on top. The y to the 1/3 will go on the bottom. And the z to the 2/3 will go on the bottom. Now, as far as test purposes, the way you would use this in future math classes, that's good. That's fine. Alex has a tiny probability of giving you shit for it, though. And that is because we can take those, you see how the fractional exponents have a common denominator? What that actually means is they have a common radical, and I could write them under one radical. I personally prefer the fractions. I know, one of the weird times where the fractions are actually not as ugly. But if we were going to figure out the fully proper Alex answer, so the third, the divide by 3's in the exponents become the cube root, and then it would be y z squared. And this is why I say the previous one is better. So you got to be careful about typing the fractional exponents, but it's doable. Down here, having to write the third root of a thing squared, not as nice. Still doable. But I'm also just telling you that because if you look at an Alex explanation, they might do that. And that's kind of the what's going on behind the scenes there. All right. And now I have natural logs and t's. And numbers. Numbers everywhere. So first step is power back up. I only have one coefficient, the 1/3. But still, that is our first step. So this is, for the moment, the natural log of t to the 1/3. And then we still have the other two. So the natural log of t to the 1/3 plus, I know how to deal with plus, I know how to deal with minus, so we're going to compress this into 1 right now. T to the 1/3 is going to be on top. The t squared minus 9, make sure to keep those parentheses until we're sure we don't need them. Just save math. That's on top, so it goes, that's positive, so it goes on top as a product. And then we have minus, so now we're on the bottom. T minus 3 is going to go on the bottom. And then all right. Now this one's a little more interesting because t squared minus 9 factors. So this can be simplified more as, so the t to the 1/3 is going to stay, but that t squared minus 9 is the same as, because it's a difference of squares, t and t, 3 and 3, one gets plus, one gets a minus, and woo, There's that t minus 3 on top and that lovely t minus 3 on the bottom. Bada bing, bada boom, they cancel. And so now we're left with a nicer looking, we don't have to type a fraction in the whole logarithm now. So it's just the natural log of t to the 1/3 times t plus 3. I could distribute that, but it doesn't do much. You could also just leave it. But just make sure you've got the outer parentheses. Otherwise, it's going to think that only the t to the 1/3 is in the natural log. All right. Woohoo. Yeah, I'm going to leave that next one for the change of base formula. So